Hi everyone, welcome to lecture 3.10. And in this video, I'm going to go through the second part of the carbonyl alpha chemistry section in the textbook. So we'll be going over roughly sections 22-5, 22-6, and part of 22-7. So basically what we're going to be doing today is extending this idea that we learned last time about enols and tautomerization, and we're going to learn about a way you can actually make those nucleophiles. So that's kind of a limitation with enols, is that they're sort of minor naturally occurring components of a mixture, but like we can't really take advantage of them unless we can make them. And that's what an enolate is. It's a way we can make that nucleophile at the alpha position. So that's what we're going to learn about is enolate ion formation, the reactivity of enolates, and then some specific reactions for them. So with that, let's get started. So an enolate is a species that is generated when you deprotonate the alpha hydrogen next to a carbonyl. So I've drawn a carbonyl here. This could be an aldehyde or a ketone, but it also could include esters and amides or carboxylic acids. And if we have a base present with sufficient strength to remove that alpha proton, that's exactly what can happen. And that is what leads to the generation of an enolate. So you might have noticed that there's a resemblance between an enolate and an enol. And that's true. An enolate is essentially an enol that has been deprotonated. That leads to an enolate having a negative charge by comparison with an enol, which is neutral. So while enolates do look like enols, they're very different in a number of ways. First of all, there are a lot more reactions that occur from enolates than there are from enols. So for example, like for the rest of the semester, I think all of the reactions that we are going to learn about, well, if not all, then most of all the reactions we're going to learn about are actually the reactions of enolates. They're of fundamental importance in organic chemistry. And we don't see that for enols. We see maybe a few pages of reactions out of the whole book. So what makes enolates so special? Well, it turns out that enolates are special and important, I would say more important than enols, because we can make them. Now, enols naturally occur in a very small proportion of any sample of carbonyl, but an enolate we can make 100% from the carbonyl when we choose. And we can do that because we can deprotonate the alpha hydrogen. So let's talk about the acidity of that alpha hydrogen for a minute. All right, so the alpha hydrogen pKa range for a typical carbonyl system ranges from about 20 to about 30, depending on the type of carbonyl. How does that compare with other types of hydrogen atoms, pKas? So I'm going to actually show you one that I think is a good comparison, is the allylic hydrogen, which has a pKa of about 45. Now you might be asking yourself the question, why is he comparing an allylic hydrogen to the alpha hydrogen of a carbonyl? Well, actually, I think there is a good structural comparison between these two. Notice that the allylic system has a pi bond, but it's between a carbon and a carbon. And of course, the carbonyl also has a pi bond, yet it is between a carbon and an oxygen. So let's compare the pKa's for the alpha hydrogen. The allylic alpha hydrogen, that's the hydrogen that's alpha to the pi bond, has a pKa of 45. The hydrogen that is alpha to the carbonyl, however, has a pKa of 20. So the difference in acidity between these two structures, the carbonyl and the allylic system, is a difference of about 20 orders of magnitude in acidity, which is a very large jump from the allylic to the carbonyl. And it begs the question, why are carbonyl alpha hydrogens so much more acidic than their counterparts in the allylic system? And it has to do with the presence of the oxygen atom. The oxygen atom stabilizes the negative charge that would result if you deprotonated it, whereas the allylic system doesn't have that stabilizing electronegative atom on it. So just the presence of that oxygen alone creates a conjugate base that is much more stable. So not all carbonyl systems have a pK of around 20. As I was saying earlier, the range is about 20 to 30. And that can make a difference on the side of when you choose your base, like which base you want to use for what substrate. I'm going to list a few of the most common carbonyl systems and their pKs, approximate pKs here. So we see aldehydes and ketones are about 20. Esters are a little less acidic with a pK of about 25. Amides are a little less acidic than that with a pK of about 30. And while you might not think of a nitrile as a carbonyl, it actually is, as we saw in our chapter on carboxylic acid derivatives. And its alpha hydrogen, which I've shown with the little H attached there, is a pK of about 25. So they're very similar to esters. And then finally, we get to the beta dicarbonyl species, which have a much lower pKa, with a pK of from about 10 to about 13, depending. You should ask yourself the question, why is it so low for those substances? Now let's take a look at the mechanism for the formation of enolates. The mechanism for enolate formation is quite simple. A base deprotonates the alpha hydrogen, which results in the electron flow as shown here. So we end up breaking a sigma bond and a pi bond while creating one new pi bond. Let's draw that resulting structure. So this is our enolate as well as the conjugate acid of the base. Now that's the normal mechanism that we show. I want to also take a deeper look and look just a little bit at how the bonds are changing and their orientation inside of the transition state or nearby the transition state. So what I've drawn here is the carbonyl system with the CO pi bond. We can see the p orbitals in yellow. And we also see the alpha carbon that is projected towards us. It's in an sp3 arrangement at the moment with its approximate 109.5 bond angles. Now what we're going to look at is what happens when the base comes in. And the first thing we want to kind of think about is that the carbon, that is the alpha carbon, the sigma bond between it and the carbonyl carbon can rotate. Now inside the transition state, the ideal setup for the mechanism is when that hydrogen, the alpha hydrogen, sigma bond overlaps with the pi bond on the carbonyl carbon so that the electrons can migrate into the newly forming pi bond between the alpha carbon and the carbonyl carbon. And so the base can deprotonate that alpha hydrogen, and the electrons in that sigma bond migrate to become a new pi bond. So let's draw a similar sort of orbital perspective drawing of the resultant enolate. So I've drawn the carbonyl system in the same orientation, where we have the carbonyl CO that will have a pi bond, and then we have the alpha carbon, which is still projected towards us. That will now be sp2 hybridized. So let's draw all of the p orbitals across the entire system now. So as you can see, there is a fully conjugated pi system through all three atoms, the carbonyl oxygen, the carbonyl carbon, and the alpha carbon. So we have a delocalized place for the electron to go. And one of those atoms is highly electronegative, thus stabilizing the electrons at that oxygen or at the alpha carbon. Now, the next thing we need to look at is what bases are required to form this enolate so that we can use the enolate. And ideally, we want to choose a base that's going to convert all of our carbonyl into 100% of it into enolate. We don't want like 5% enolate or 10%. We want 100% enolate. So that involves choosing the correct base for quantitative enolate formation, which is what we're going to look at next. So as we've seen, enolate formation is just an acid-base problem. So we need to treat it like an acid-base equilibrium issue, which it is. So let's look at how we decide what base to use based on our knowledge of acids and bases. So what we do is we look at both sides of the equilibrium and we find the acid. And on the other side, we need to find the conjugate acid, and we need to identify their pKa values. So our acid is just the carbonyl, which has a pKa of about 20. Now, the conjugate acid, well, the pKa of that is going to depend largely on what base we chose, right? So depending on the base we choose, we will get a different pKa value. Now, here are some different scenarios of what type of conjugate acid pKa do you need to get a different situation or result. So for example, if our conjugate acid pKa is less than 20, what side does the reaction favor? Well, remember that in an acid-base equilibrium, you will always favor the side with the weaker acid. And remember, larger pKa values are weaker acids. Smaller pKa values are stronger acids. So if the conjugate acid pKa is less than 20, that side would be the stronger acid. So the reaction would favor the left. Now, what would happen if our conjugate acid pKa was around 20? So say like, I don't know, within a few units of 20, maybe like 15 or 25. What would we expect to happen then? Well, that would mean that the conjugate acid had a pKa that was very similar to our acid on the left, our carbonyl. And for that matter, we wouldn't really see a big shift towards either side. We would have a close to 1-to-1 ratio or thereabout. So we wouldn't see 100% conversion to one side or the other. This is also not a desirable situation. Now, what if the pKa of the conjugate acid was greater than 25 or 30? Well, what that would mean is that the conjugate acid would be a much weaker acid than our carbonyl, which should say that the reaction should definitely strongly favor the forward direction towards the much weaker acid. And that's exactly what would happen. So now let me walk you through some of the most common bases that we see being used for enolate formation. This is for quantitative enolate formation. So when we want to make 100% enolate from our carbonyl. Probably the most common base we see in quantitative enolate formation is one where we have an amine that has been deprotonated. So an amine itself has a pK of about 35. So that means the conjugate acid of this amide, this deprotonated amine, has a pK of 35, which is sufficient for our need to make a quantitative enolate because the conjugate acid of this base is 15 orders of magnitude weaker than our carbonyl. Now, of course, there are several different possibilities for amides that you can choose. The simplest is where the R groups are just hydrogen atoms, and that would be like lithium NH2, lithium amide. That can be made from ammonia by deprotonating it with a very strong base. And that's used occasionally with these reactions, but probably a lot more common is the molecule lithium diisopropyl amide, or LDA. And in LDA, the R groups are isopropyl. That's why it's called lithium diisopropyl amide. Now, while LDA is very common to see, there also are a few other choices in bases, which can become important, as you will see. Sodium hydride is definitely an alternative choice. It's very small and functions as a great base. Alk oxides might be considered, however, their pKa for the conjugate acid is like 15 to 20, so they're not good for carbonyls that have a pKa of 20. They're only good for carbonyls that have a pKa that's less than 13 or so like a dicarbonyl species. So let's go to the next page and draw some different enolate examples. So take a few moments and try drawing the enolate for each of the example molecules shown here. So you're going to find the alpha carbon, remove the alpha hydrogen, and draw the enolate as I've shown next to the molecule. Now, in some of these examples, you will see, hey, maybe there's more than one alpha carbon. If there are more than one, then draw both enolates. So as we saw above, there are definitely situations in which you will have more than one alpha carbon, and therefore the choice of which enolate is preferred at equilibrium is a good question to ask. And that brings us to the question that I have shown here is, if two enolates are possible, because we have an unsymmetrical carbonyl, how can you know which enolate is favored under a given set of conditions? And that's what we're going to look at next. So in this example, I have two alpha hydrogen atoms because we have two alpha carbons. Now let's consider the enolate from both of these alphas. So I'm going to draw the enolate for alpha 2 over here. And then on the other side, I will draw the enolate for alpha 1. Now, looking at these two enolates, the one from alpha 2 and the one from alpha 1, is there anything we can say about the differences between them? Well, notice that the one from alpha 1 has a pi bond that is more substituted than the one from alpha 2. And you might recall from learning about alkenes that alkenes are more stable when they're more substituted. So I think it would be fair to say that the one from alpha 1 is a more thermodynamically stable enolate than the one from alpha 2. Now, the other thing to realize is that the enolate from alpha 2 has a lower kinetic energy barrier to get to it. It has a lower energy of the transition state. And that's because the alpha hydrogens, the ones that are being deprotonated, are more accessible in the one from alpha 2 because the pi bond is less substituted, for the exact opposite reason that alpha 1 is more stable. So we can say that alpha 2 is less hindered, and also statistically speaking, there are more alpha hydrogens on the one from alpha 2. So statistically, it's more likely to be deprotonated, which also lowers the kinetic energy barrier. So we can say that the one from alpha 2 is the kinetic product, the one that's formed faster, and the one from alpha 1 is the more thermodynamic product, or the thermodynamic product because it's more thermodynamically stable. So as you've learned with reversible reactions, it's possible when you have a kinetic and a thermodynamic product to sometimes control which one you will form, preferably. And we learned about kinetic products are favored in reversible reactions when you have colder temperatures, because you don't have enough energy, you're not providing enough energy to get over a higher activation barrier. So you favor the lower activation barrier product, which would be the kinetic product. Similarly, if you want to get the thermodynamic product, you would use warmer temperatures. So I'm also making mention here of the size of the base. A bulky base favors the kinetic product because of its large steric demands, whereas a less bulky base would be favoring the thermodynamic product. Typical cold temperatures are minus 78 degrees C, while warmer temperatures are anywhere from like 0 degrees C to room temperature. The base that's, I would say, kinetic would be LDA, and the base that's small or thermodynamic would be sodium hydride. So those are the conditions for kinetic and thermodynamic enolate formation so that you can control which enolate you form, which becomes very important. So now that we have a pretty good understanding of enolate formation, we can now start learning about the reactions of enolates. So that's what we're going to do starting on the next slide for, I want to predict basically the rest of the semester. We're going to be looking at different examples of reactions of enolates. So let's get started with that. So as far as reactivity goes, enolates are nucleophiles. They're nucleophilic at carbon, at the alpha carbon, but they're also nucleophilic at the oxygen. And that's unlike with enols, because enols didn't have that negative charge on them to delocalize to the oxygen. So I'm going to show you the resonance hybrid here. I'm showing you the resonance from the electron being negative to the carbon being negative. So we can see the electrons being localized on carbon or localized on oxygen in both resonance forms. But realize that in the true enolate, it's not either of these, it's both. So a resonance hybrid would look something like this. We see a delocalized pi bond from the oxygen to the carbon, making the oxygen delta negative and the carbon delta negative. So it's nucleophilic at both of those positions. And because of that, an electrophile can react with either the oxygen or the alpha carbon. Now, it turns out that electrophiles definitely tend to add more, you'll see more commonly to the carbon than to the oxygen. But both are possible and both are used in synthesis. So if we add an electrophile to the oxygen, we get an enol derivative, where we have some E that's attached to oxygen. I'll show you an example of that below. But if we react the electrophile at the alpha carbon, we get a alpha substituted carbonyl derivative. So now let's take a look at some examples of both of these reactions. I'll show you three. I'll show you alpha halogenation, sialyl enol ether formation, and the haloform reaction. So just like the reaction we saw with enols, it's possible to take a carbonyl species that is enolizable, so it has an alpha hydrogen, treat it with a base and halogen, like Br2 or Cl2, and get an alpha halogenation. Now, while possible, this is not practical, because one of the problems is that the resultant alpha halogenated carbonyl can still react as an enolate if it has an additional alpha hydrogen. So if you have more than one alpha hydrogen, you will get successive, or what they say, exhaustive halogenation, and you'll get a mixture of all different types. So monohalogenation is really only possible if you only have one enolizable proton. Now, another example, and I don't think this is shown in the book, is the production of sialyl enol ethers. A sialyl enol ether is prepared starting from an enolizable carbonyl and treatment with a base like LDA to produce the enolate, and in a second step, a sialyl chloride, so like trimethyl sialyl chloride, is added. And it turns out that the silicon, that sialyl, reacts with the oxygen. So this is an example of reactivity at oxygen instead of at carbon. And these sialyl enol ethers are useful in synthesis because they're kind of like enols, and they react like enols, and they can be isolated unlike enols. Another example is the haloform reaction. Haloform reactions are kind of specific to methyl ketones. So that's where we have three alpha hydrogen atoms. So we can do an exhaustive halogenation of a methyl ketone with this reaction. And it works like this. You basically do exhaustive halogenation, so treatment with bromine or chlorine or iodine and a base. The products of this might look a little bit unexpected at first. I've drawn a carboxylic acid here, but realize it's in basic conditions, so that would actually be a carboxylate, so it would have a negative charge there. So we get the carboxylate and haloform, which is like CH with three halogen atoms on it. So I'm showing you a few, like bromoform, chloroform, and iodoform. That's produced. And those haloform, especially in the case of iodoform, have colors associated with them. So this haloform reaction is often used as a qualitative visual test for a methyl ketone. You take a small amount of a methyl ketone, treat it with X2 and sodium hydroxide in a test tube, and then if you see like a yellow solid precipitate, then you know that you had a methyl ketone. This is obviously if you don't have access to like an NMR or something like that, which was very necessary up until recently for most people studying organic chemistry. We had to do reactions like this. So let's turn the page and look at one last reaction of enolates for today. So because we have a nucleophilic carbon on an enolizable carbonyl, that means we can make carbon-carbon bonds between the alpha carbon and some alkyl group. And we can do this using an SN2 reaction. This is known as the enolate alkylation reaction, and it works like this. Step 1, we treat our enolizable carbonyl with a base, such as LDA or sodium hydride, and the right conditions if we want kinetic or thermodynamic. And then in the second step, we use a primary alkyl halide or alkyl tosylate. something with some alkyl group that's primary that has a good leaving group on it. And what happens is an SN2 reaction between that alpha carbon and that R prime X. And that produces the carbon-carbon bond. Now let's just take a quick look at the mechanism. So you can see we form the enolate with the base, and then we just do an SN2 reaction at the alpha carbon to make that alpha carbon-carbon bond. Let's look at a few examples. All right, so if we look at the substrate, we have a ketone. It's cyclic, and it has a cyclohexane ring attached to another cyclohexane ring. So if we look at this, we identified two alpha carbons, alpha 1 and alpha 2. Now we're treating this with LDA, a bulky base, with cold conditions. So that tells us we are running under kinetic conditions. So we have to think about, well, which enolate we would form. Well, that would be the kinetic enolate, which would be the less substituted enolate. Now the second step, we are treating this with an allylic bromide. So the SN2 reaction will take place at that carbon atom attached to the bromine. Let's draw the product. So that would be the result under the kinetic conditions. We would assume that we would form the kinetic enolate, and we would do the SN2 reaction at that alpha that's less substituted. Let's take a look at another example. Now, this is a little bit of a tricky example because you haven't seen anything like this before. In step 1, instead of me adding a base, I've added a Gilman reagent. And in step 2, I add my primary alkyl halide. And this is the product that we would get. It's this ketone with the ethyl group at the alpha position and a methyl group at the beta position. What I want you to do is figure out or determine the mechanism for this. Like, how is this happening? So try to work on that. I will post something so that you can see, or you can ask me about it. But I think you can figure out this mechanism. Look back at what you know about Gilman reagents and how they react with molecules like the starting material I have shown here. So that's going to wrap up the video for today. Next time we will look at 2 additional reactions of enolates, but we will focus in on a special type of enolate, one that has a much lower barrier to entry with a lower pKa value of the carbonyl. So we'll look at the malonic ester synthesis and the acetoacetic ester synthesis, and we will see how we can synthesize pretty much any carboxylic acid or ester that we would ever want to make. So that will be next time. I hope you guys are doing well. Let me know if you have any questions.